For decades, the consensus on our origins has been straightforward. Roughly 3.8 billion years ago, the first sparks of biology ignited in Earth's primordial oceans. But geologically speaking, that timeline is problematic. Early Earth was a hostile, volcanic environment. It was constantly bombarded by heavy asteroids, making it incredibly difficult for fragile, single-celled life to take hold and survive. Look next door to early Mars, however, and you find a very different environment. Long before Earth settled down, Mars was a warm, wet oasis with rivers, lakes, and a thick, protective atmosphere. This leaves us with a chronological paradox. The environment capable of supporting early life appeared on Mars millions of years before the actual biological timeline began on Earth. Recent discoveries throughout 2025 and 2026 are offering a specific solution to this timeline gap. The data points to a distinct sequence of events. The earliest life forms didn't spark on Earth at all. They originated on the red planet. While this might sound like science fiction, an increasing number of planetary scientists and astrobiologists are treating it as a highly probable reality. To understand how this works, we need to look at the physical evidence that connects these two planets, starting with how a microbe could survive a trip across the solar system. The mechanism driving this planetary exchange is known as panspermia, the scientific theory that biological material can survive traveling through space on rocky debris. The process requires extreme force. When massive asteroids collided with the Martian surface billions of years ago, the sheer kinetic energy ejected tons of rock and soil outward, escaping the planet's gravity entirely. If those Martian rocks harbored microscopic life, those organisms could essentially hitchhike through the freezing vacuum of space. Eventually, some of that debris survived the fiery atmospheric entry and crash-landed here on Earth. Orbital physics and biological survival tests have demonstrated that this pathway is viable, providing the physical opportunity for life to migrate between neighboring worlds. We know this migration happens because we possess the physical evidence. Researchers have successfully recovered confirmed Martian meteorites right here on Earth. When astrobiologists examine the internal structure of these specific rocks, they find complex chemical signatures that closely mirror the byproducts of biological processes. These specimens serve as hard, tangible proof that material from the Martian surface reaches our planet completely intact. This physical evidence is now backed up by direct analysis from the source. In 2026, we received critical new data from the Perseverance rover's drilling operations on the Martian surface. The soil samples revealed dense clusters of organic molecules and distinct structural formations that point to the existence of ancient microbial life. These findings support the possibility that Mars was already hosting biological activity, while Earth was still a cooling, chaotic mass. Our own biology offers a different window into this history. Recent genetic research has focused on comparing the DNA of Earth's oldest life forms against planetary environmental markers. Researchers found that the specific genetic sequences in early Earth biology align with theoretical models for a Martian origin, rather than a spontaneous Earth-based evolution. When you combine the geological timeline, the astrophysics of planetary ejecta, and these new genetic markers, a unified, multidisciplinary case for panspermia comes into focus. Naturally, there is still debate. Many researchers maintain a healthy skepticism, noting that the existing meteorite chemistry and rover organics currently represent strong circumstantial evidence. But it is exactly this debate that is driving space agencies around the world to prioritize Mars sample return missions above all other deep space exploration. Retrieving pristine rocks directly from the Martian crust and studying them in full-scale Earth laboratories will provide the definitive test. It will either validate the Martian origin theory or require a complete rethink of our biological history. The implications of this research extend far beyond our own solar system. If life is resilient enough to endure the brutal physics of an asteroid impact and span the void between planets, then biology is likely far more common across the universe than we previously estimated. If this transfer occurred, it would mean that every living organism on our planet, from deep-sea ecosystems to human beings, shares the same ancient Martian lineage. It invites us to pause and consider what it actually means to carry a microscopic piece of another world inside our very DNA. Humanity has spent decades scanning the stars for signs of alien life.